Mechanical Mixing Unit, MMU. The mechanical mixing unit is designed to reduce inherent control coupling. Inherent control coupling might be referred to as a side effect of control input. You increase collective to bring the aircraft up to a hover. However, the side effect of this is the increased torque causing the nose to turn to the right. This is an average mixing for all flight conditions, is not based on any particular weight. The pilot, with assistance from the AFCS, will make the adjustments needed if these mixings are too much or too little. The mechanical mixing unit helps reduce pilot workload through the following inputs and outputs. Collective to pitch. Mixing compensates for downwash on the aft portion of the fuselage and stabiloider. As collective is increased, the main rotor disc is tilted forward slightly, and as collective is decreased, the main rotor is tilted aft slightly. Collective to roll. Mixing compensates for translating tendency. As the collective is increased, the main rotor disc is tilted slightly left, and as the collective is decreased, the main rotor disc is tilted slightly back towards the right. Collective to yaw. Mixing compensates for the torque effect of the main rotor. As collective is increased, tail rotor pitch is increased, and as collective is decreased, tail rotor pitch is increased. Yaw to pitch. Mixing compensates for tail rotor lift vectors. As tail rotor pitch is increased, the main rotor disc is tilted slightly aft, and as tail rotor pitch is decreased, the main rotor disc is tilted slightly forward. The tail rotor on the UH60 is mounted to provide a vertical lift component to help offset aft CG component associated with the airframe design. In the four mechanical mixings, the first word in the title is the pilot input to the flight controls. The second word is the mixing unit output to the flight controls. Electronic coupling. Collective and airspeed to yaw. This input is additional to collective to yaw mechanical mixing. The system design is a compensation for the rotor system torque effect caused by the changes in collective position. The flight control computer, number 2 flight control computer or FCC, commands the yaw trim actuator to make a change in the tail rotor pitch as the collective position changes. The components of this system have the ability to decrease tail rotor pitch as airspeed increases. The change is necessary because of an increase in tail rotor and cambered finish efficiency. When airspeed decreases, the opposite input occurs. The amount of tail rotor pitch change is proportional to airspeed. Maximum input with this system occurs from 0 to 40 knots. As airspeed increases above 40 knots, the amount of input will decrease. At 100 knots airspeed and above, no inputs are required from this system. Electronic coupling is reduced as airspeeds increase from 40 to 100 knots. Above 100 knots indicated airspeed, electronic coupling is reduced to 0. Automatic flight control systems. AFCS enhances the stability and handling qualities of the helicopter and provides autopilot functions. The AFCS is comprised of 5 basic subsystems. Stability Augmentation System, also known as SAS, provides short-term rate dampening in pitch, roll, and yaw axis for stability. Trim provides control position and force gradient functions. FPS provides basic autopilot functions when coupled with trim. Coupled Flight Director provides a means for the pilot to select defined autopilot functions, automatic flight control positioning, and provides steering cues for display on the MFD when it is coupled. Stabilator improves flying qualities with the use of electromechanical actuators in response to collective, airspeed, pitch rate, and lateral acceleration inputs. Flight control computers. The central component of the AFCS is 2 redundant flight control computers. Each computer receives signals from the pilot's controls, motion sensors, accelerometers, control panels, avionics systems, embedded GPS and inertial navigation systems, and air data computers to compute commands which are sent to the cockpit, trim actuators, SAS actuators, and stabilator actuators. The number 2 FCC is the only FCC that sends signals to the trim actuators for dynamic flight control inputs. The number 1 FCC used to be the number 1 control actuator, but now is no longer that for this version of the aircraft, and number 2 FCC, which is used for controlling the number 2 actuator, are used in the stabilator system. The FCCs are responsible for processing signals for airspeed, lateral acceleration, collective stick position, and pitch rate data. The FCCs contain power supply, actuator drive circuits, processing, and feedback circuits, as well as fault monitoring circuits. By communication over the cross-channel data link, CCDL, of automatic mode engagement, each FCC will know the status of the other FCC. When one fails from loss of power or fault detection, automatic mode will be disengaged. Lateral, longitudinal, and vertical accelerometers provide information to the FCCs concerning aircraft acceleration and deceleration. This information is then processed for use by the AFCS to improve aircraft stability. Collective stick position sensors are operated by movement of the collective linkage and send a signal to the FCCs indicating collective stick position. The number 1 and number 2 collective stick position sensors generate an output signal proportional to the collective stick position. This information is used to help determine the stabilator position. Additionally, the same signals are used for other aircraft systems in the UH60 mic. Trim servos are used in the pitch, roll, yaw, and collective to allow FPS and coupled flight director to make necessary inputs to maintain desired pilot selections. Air data computers, also known as ADCs, provide airspeed, barometric altitude, barometric rate information to the FCCs. The ADCs connect to the pitot-static system. Both provide data that contains information concerning the helicopter's airspeed, altitude, and altitude rate. The stabilator uses the airspeed data. The airspeed data for the number 1 FCC is generated by the number 1 ADC. The airspeed data for the number 2 FCC is generated by the number 2 ADC. An ADC is located on each side of the forward cabin in the flight control broom closet. The Embedded Global Positioning and Inertial Navigation Unit, also known as EGI, replaces the directional gyro. Pilot and co-pilot vertical gyros, compass control panel, and compass flux valve, as is found on the earlier versions of the Black Hawk. The primary function of the EGI is to compute attitude, heading, present position, and turn rate data. This information is provided to the FCCs from 2 self-contained EGI systems consisting of an inertial navigation system and embedded global positioning receiver. Each EGI provides data that contains information concerning the pitching rate of the helicopter. The pitch rate data is then used by the stabilator to enhance the AFCS system's ability to correct short-term pitch disturbances. Both the inertial and GPS determine their position independently. The GPS determines position from the GPS satellite constellation. The GPS receiver determines 3-dimensional worldwide position coordinates. The GPS provides for all-weather continuous operation based on the principle of satellite ranging. Satellite ranging is the process of measuring the time satellite signals take to travel from the satellite to the helicopter GPS antenna. By ranging to 4 satellites, 3-dimensional positioning is easily able to be determined. The inertial position is determined by speed and heading integration over time applied to a known starting position. For inertial navigation systems to work correctly, it must have a known starting location. Normally, this is provided by the GPS unit. Both the GPS and inertial systems locations are compared by the EGI for relative errors to determine the rate of correction required for inertial position. These corrections are applied to provide blended position data. Inertial systems are generally self-contained and do not emit an external signal. However, their accuracy can drift, and if not maintained in the event of GPS failure or loss of satellite constellation, navigation could continue with the inertial system alone. However, updates for the inertial system would be required. The EGI provides information for other aircraft systems to support navigation, time distribution, flight control, and primary flight displays. Navigation signals provide navigational information to the pilots through the MFDs and provide reference to control attitude, and heading of the aircraft through automatic flight control systems. The flight control computers command inner loop SAS actuators and outer loop trim actuators in pitch, roll, and yaw control channels. The computers also provide self-monitoring, fault isolation, and failure advisory. The inner loop SAS employs rate dampening to improve helicopter stability. This system is really fast in response, limited in its authority, and operates without causing movement of the flight controls. The outer loop, trim, provides long-term inputs by trimming the flight controls to the position required to maintain the selected flight regimen. It is capable of driving the flight controls throughout their full range of travel with 100% authority at a limited rate of only 10% per second. Both inner and outer loops allow for complete pilot override through the normal use of the flight controls. The FCCs process incoming information from various sensors aboard the aircraft for use by the Computer Central Processing Unit, CPU, to compute required corrections. Inner loop correction signals are routed to the SAS actuators, and outer loop signals are routed to trim servos and actuators. Stability Augmentation System, SAS. The UH60M incorporates 2 SAS systems to help maintain a stable platform in flight. SAS responds to short-term aerodynamic disturbances such as wind gusts or up and down drafts by effectively dampening any helicopter movement. Since responses to disturbances are almost instantaneous, the SAS control is limited in its authority or amplitude in order to prevent SAS malfunctions from causing undesirable helicopter responses before the pilot has a chance to react and take control. SAS enhances dynamic stability in the pitch, roll, and yaw axis. This prevents pitching in the longitudinal axis, rocking in the roll axis, and fishtailing in the yaw axis. SAS also enhances turn coordination at airspeeds greater than 50 knots. SAS-2 enhances turn coordination by deriving commands from lateral accelerometers, which together with roll rate signals are sent to the respective yaw channels automatically at airspeeds greater than 50 knots. The FCCs receive the respective on-side EGI signals for SAS actuator movement. A malfunction may be detected as an erratic motion in the helicopter. If the malfunction is of an intermittent nature, the indication can be cleared by pressing Failure Reset Computer 1 or Failure Reset Computer 2 switches. If the malfunction is continuous, the appropriate SAS should be turned off, in which case the SAS degraded advisory will appear on the ECAS display. With SAS1 or SAS2 off, the gain of remaining SAS is doubled. Doubling the gain simply means that the sensitivity of the remaining SAS module has been doubled. SAS actuator hydraulic pressure is monitored. In case of loss of SAS actuator hydraulic pressure, or if both SAS1 and SAS2 are turned off, the SAS off indication will appear on the MFD. In the latter case, FPS will automatically turn off and FPS on segment lights will extinguish. SAS degraded advisory will appear when the pitch, roll, and or yaw SAS channels from SAS1 or SAS2 has disengaged due to fault. Trim system. The trim unit provides cyclic, pitch and roll, pedal, yaw, and collective flight control position reference and control gradient. It maintains the cyclic stick, tail rotor pedals, and collective stick at a desired position. Each trim actuator and servo contains a force gradient spring to permit pilot override of trim reference. The trim units may be 100% overridden through use of the flight controls. Trim is engaged by pressing the trim switch on the stabilator/automatic flight control panel. The trim system consists of the following: pitch trim servo, roll trim actuator, yaw trim actuator, collective trim actuator, cyclic trim. The cyclic trim is a four-way trim switch on each cyclic stick that establishes a trim position without releasing trim. With trim engaged, the trim position is moved in the direction of switch movement. The cyclic is moved by the cyclic trim switch in one direction at a time. When FPS is engaged, the cyclic trim switch changes the pitch and roll attitude reference. Cyclic trim activation in any of the four directions trims the cyclic stick towards the desired location. Release of the cyclic trim stops cyclic movement. An additional movement of the cyclic trim beeper is the Z-axis or plunge feature, also known as Z-axis plunge. The plunge feature is activated by simply pushing in on the trim switch. If the aircraft is hovering when the plunge feature is selected, automatic radar altitude engagement will come on the FD-DCP will be maintained, and you will maintain a hover over the selected location. The hover mode has three states: velocity hold, also known as hover velocity hold, position hold, also known as hover position hold, and deceleration mode, also known as hover decel. The hover mode will always attempt to engage coupled on a coupled FD. If neither FD is coupled, the FD will attempt to engage hover on the FD on which the mode was selected from the FD DCP or cyclic trim switch. If the plunge command is selected above 60 knots, a barometric altitude engagement on the FD DCP will occur instead of radar altitude. In this mode, the plunge command will engage in airspeed mode of 80 knots, and if between 60 to 80 knots, 120 knots, if above 120 knots, and current airspeed is below 80 and 120 knots. A heading change can be commanded through the use of four-way AFCS trim button switch on each collective stick. Actuating the switch left or right below 50 knots will cause the tail rotor pedals to drive until the helicopter attains a yaw rate of approximately 3 degrees per second, also known as a standard rate turn. When trim is released, heading hold is re-engaged to hold new heading. Actuating the trim switch down or up will adjust the reference altitude for collective flight. When trim is released, altitude hold is re-engaged to hold the new altitude. The collective AFCS trim button is deactivated anytime the heading hold mode is engaged. Flight Path Stabilization, FPS. Flight path stabilization provides basic autopilot functions in the pitch, roll, and yaw axis. Proper operation of FPS requires that the SAS boost, trim, and SAS1 as well as SAS2 functions be selected on the AFCS panel. Performance of the system will be improved by proper operation of the stabilator in the automatic mode. The design of the system is such that the FCCs go through the following. Below 50 knots and above 50 knots, attitude hold below 50 knots for pitch, above 50 knots for attitude hold and airspeed hold, attitude hold below 50 knots for roll, as well as attitude hold above 50 knots, heading hold for yaw under 50 knots, as well as heading hold and turn coordination when above 50 knots. To make that more simple, above 50 knots, you will have pitch, attitude hold, and airspeed, attitude, roll, and attitude hold, heading, hold, and turn coordination via yaw. Reference the chart associated on page 22 of the Flightline supplement to look at that more simply. FCC2 provides FPS command signals to the pitch, roll, and yaw trim actuators, which in turn reposition the flight controls. The AFCS provides command signals to the trim actuators to reposition the flight controls using the trim system. Trim is the muscle in the system. The AFCS moves the flight controls through the use of trim and allows the aircraft the ability to fly and maintain a predetermined flight profile. The number 2 FCC has sole input to the UH60M trim actuators. All commands to move the trim actuators are provided by the number 2 FCC. Flight path stabilization. Roll. Automatic turn coordination is provided at airspeeds greater than 50 knots. The turn coordination allows the pilot to fly a coordinated turn with directional control provided by the FCS. Automatic turn coordination is engaged and heading hold disengaged when roll attitude is greater than 1 degree for any of the following conditions. Lateral cyclic greater than 1/3 inch stick displacement from trim. Cyclic trim release is pressed. Roll attitude is beeped beyond the 2.5 degree bank angle. Actuation of the heading trim switch above 50 knots uncoupled in the lateral axis for more than 1 second provides a 1 degree per second coordinated turn. Heading holds automatically re-engaged and turn coordination disengaged upon recovery from the turn when the lateral stick force, roll attitude, and yaw rate are within prescribed limits. Alternately, pressing and holding the AFCS collective trim button left or right will initiate a standard rate turn on the roll axis at airspeeds above 50 knots. Note, it is possible to have turn coordination below 50 knots. To achieve this, the aircraft must go into a coordinated turn above 50 knots and then decelerate below 50 knots. If the aircraft is placed into a turn below 50 knots, it will skid and not achieve turn coordination as a result of the heading hold. Flight path stabilization yaw. The yaw axis of FPS provides heading hold at airspeeds less than 50 knots and heading hold or turn coordination at airspeeds greater than 50 knots. For heading hold operation at airspeeds less than 50 knots, the helicopter is maneuvered by the desired heading with feet on pedals. When trimmed at the desired heading, the pilot may remove feet from pedals, at which time the existing heading becomes the reference heading, which is automatically held. The weight on wheels switch disengages heading hold when the helicopter is on the ground, with FPS on. Below 50 knots, the 4-way AFCS collective trim button may be used to slew the reference FPS heading to the desired heading. If a malfunction is detected, the FPS fail caution light on the ICAS will illuminate. The FPS will either continue to operate in degraded mode, such as without heading hold, or may cease to function altogether. In this situation, the pilot must take over manual flight of the helicopter and may either turn off the FPS or evaluate performance to determine the degree and type of degradation and